Welcome to the NASA Ames 2016 Summer Series. 2 questions. How does the microscopic world inform the macroscopic world, and vice versa? What could we learn, and how do they interact? Can we use quantum mechanics to advance real-world applications? Today's seminar, entitled Quantum Mechanics at Macroscopic Scales, will be given by Dr. Mark Kasevich. He is a professor of physics and applied physics at Stanford University. He received his Bachelor's of Arts in Physics from Dartmouth, followed by a Master's in Physics and Philosophy from Oxford University as a Rhodes Scholar, and then a PhD in Applied Physics from Stanford. His current research is centered on the development of quantum sensors of rotation and acceleration based on cold atoms. He has published numerous publications in really relevant journals, including Nature and so on. And in his spare time, co-founded AOSense Incorporated, a developer and manufacturer of innovative atom optic sensors for precision navigation, time and frequency standards, and gravity measurements, and currently serves as the company's consulting chief scientist. Please join me in welcoming Dr. Mark Kasevich.
Thank you. Thanks for the introduction. It's great to be here this morning. So I'm going to tell you about experimental work coming out of my laboratory at Stanford, just up the road, where we're trying to push the boundaries of quantum mechanics to understand to what scales we can accept that quantum mechanics will be true. And when I say scales, I'll kind of orient you to my interest in that as the talk goes on. But I think it's no secret that quantum mechanics, probably one of arguably the most successful physical theory we have, that had its birth in the early 20th century, has left us puzzled. And many of us who practice it, both by experiment and pencil and paper work, find points where it just doesn't seem to make sense. And oftentimes that boundary becomes most puzzling when you ask, does quantum mechanics manifest over the distance scales and time scales of everyday life, meters and seconds and large numbers of particles? And so I'm going to tell you about experiments today where we're trying to find quantum systems that we can explore on meter scales and with large numbers of particles and so forth. Our dream would be to explore, quantum mechanics of humans being in 2 places at once, but we're nowhere near that. But what we have managed to do is to manipulate atoms in such a way that they can exhibit surprising quantum mechanical attributes. So let me introduce you to the field that I'm in. I'm an atomic, molecular, and optical physicist. And back in the early 90s, there was some incredible work that came out of the Constance atomic physics group. And what they did, Jürgen Winnick and his colleagues did, is they did something analogous to the Young's double slit experiment, but they used helium atoms. And the way this experiment worked is they took a beam of helium, which is at this part of the diagram, and they took these atoms and they fired them at a narrow slit. Now, if you're thinking classically, the atoms just go through the slit, and the slit kind of defines an atomic beam. If you're thinking quantum mechanically, and you're a believer in the de Broglie relationship, namely that atom really could be considered a wave whose wavelength is Planck's constant divided by its momentum, then you expect wave-like behavior. And by design, Winnick's group made this slit narrow enough so that the helium atom waves diffracted into this coherent set of wavefronts, much like you would see a beam of light diffract as it propagates through a slit in a laboratory experiment, and such that it coherently illuminated 2 more slits, this location and that location. Well, those 2 slits now become sources for diffracted waves, and those waves overlap at a detection screen here. Now, if they were water waves or light waves, you would have no problem accepting that those waves would interfere constructively and destructively, giving you maxima and minima in intensity. But these are atom waves. And how do the atom waves interfere? How is that interference manifested? Well, it's manifested by the constructive and destructive interference of the atomic wave functions. And according to the rules of quantum mechanics, you add the wave functions before you square, and then when you square, you get those interference patterns that you calculate mathematically. But what it really means, again, following the quantum paradigm, is that those ripples in the wave function correspond to ripples in the probability of detecting the atom at a given position along the screen. And so as they scanned their detector along this screen, they saw the following. This is the detector position, and this is the number of atoms that they detected in 5 minutes. They saw this beautiful oscillating pattern, which is just the kind of picture that you associate with the Young's double slit experiment. And when they go back and use the Schrodinger equation and so forth and calculate the periodicity of the oscillation, what you would expect from the momentum of the atom and Planck's constant and the mass of the atom, turns out it lined up nearly perfectly with this data, demonstrating that we had reached a position, or they had reached a position where they could coherently control the center of mass wave function of a beam of helium atoms. Now, this wasn't a surprise to anybody. I mean, if you believed what was written down in the early 20th century, of course, atoms, under certain circumstances, will interfere. That's the law of quantum mechanics. Electrons interfere to give us the hydrogen spectrum, and Davidson-Germer showed us diffraction from surfaces. So what's the big deal here? Well, the big deal was there were some notable physicists in the, let's say, mid-20th century who said, it's great, quantum mechanics works just fine for those electrons, for magnetic spin, and everything we know about atomic structure, but ain't nobody ever going to build an interferometer for atoms. Why? Because, well, every time you build an interferometer, one of your key engineering challenges is to stabilize the relative paths of the two interfering beams. In other words, if I go back to this slide, I have to make sure that the phase acquired by the wave that goes through this slit and hits the screen there is stable with respect to the phase that goes through that slit. And you could do some simple calculations for atoms and convince yourself that there's, maybe you could build the slits, but there's no way you'd get stable phase. There would always be some environmental perturbation which would shake one wave with respect to the next, so that pattern wouldn't be stable. Those fringes would shake back and forth, and as you waited to see the fringe emerge, you would never see anything, and that would look like just classical behavior. And so what happened was, as technology, since in the kind of mid-20th century to the early 90s, technology progressed, and we learned, the field learned how to control the environmental disturbances on in this case, the beam of helium atoms, so that you could have a stable phase. And this was the paradigmatic experiment that kind of started our field in the early 90s. So you could ask, well, technology has progressed yet again, so where are we? And I could take you through the entire 25 years, but I'll take you to a snapshot of our most recent data. Where are we today? How well can we control the trajectories of atoms, and can we see interference, and if so, over what types of distance scales and time scales? This distance scale here is measured in millionths of a meter, 10 microns. So here's some data that came out of my lab last year, and what I'm showing you is 2 ensembles of rubidium atoms. I'll tell you how we make those atoms in a moment. And these rubidium atoms, this peak here has about 10 to the 5 atoms, and this peak here has about 10 to the 5 atoms. And they're separated by a distance of more than a half a meter, basically from here to there. Those atoms are separated. That's not a big deal. But what is a big deal is that I claim each and every atom that is a member of this peak also has a partner in that peak. It's actually the same atom that's been coherently divided and put in both places at once. Now, according to the laws of quantum mechanics, when I look at a state like this, I kill it, and I collapse the state so that the atom is either in the left peak or the right peak, which is what happened when I took this picture. But before I took that picture, I claim that I had this amazing state where each and every one of those 10 to the 5 atoms was the only way I could describe physically what it was an atom that was in this place and this place at the same time. The logical progression would be putting molecules in two places at once, or human beings separated by a meter scale, and so on. But an atom I want to remind you, is a pretty complicated object, especially rubidium atom that has a grab bag of nucleons and a bunch of electrons all around it. It's not a fundamental particle. It's a big collection of fundamental particles. So obviously, my job now is to convince you that I've had atoms in two places at once. This picture alone cannot convince you of that. I might as well just put 10 to the 5 on the left and 10 to the 5 on the right. How do I convince you that there are two places at once? I have to do an interference experiment. I have to bring those clouds back together, and I have to overlap them, and I have to see them interfere as waves. And so that's the data I'll show you in the next few slides. So this is a picture of the apparatus. Let me just walk you through the apparatus before I show you some of the data. So we like to joke in my group that everything looks better in CAD. So here's the CAD rendering of the apparatus, which is in this pit in the basement of the Variant Physics building at Stanford. And it's about a 10-meter deep pit. And what you see here is magnetic shielding that surrounds an ultra-high vacuum system where we've basically pumped everything out and created an environment that if I have a rubidium atom of the appropriately conditioned state, it won't interact with or be collided with other gas elements in the vacuum system. And what we do is the following. At this location here, which is at the bottom of that pit, we use some modern atomic physics techniques to create a cloud of ultra-cold, and I'll explain what ultra-cold means in a second, ultra-cold rubidium atoms, about 1 million of them. What we do is we take rubidium from a thermal atomic source, a chunk of metal. It gets heated up. You get a stream of atoms that are moving about 200 meters a second. You capture them with laser light. The laser light is configured in such a way it cools them down to temperatures of millikelvin to microkelvin. And what we mean by that is that if I look at the kinetic energy or the velocity of one of those atoms, I measure it in units of centimeters per second. The way this was a technique that was discovered by Stephen Chu and others in the 80s and 90s, for which they received the Nobel Prize. After we cool the atoms that way, we further cool them in they're cold enough now that I can let them sit in a magnetic field, and that magnetic field serves as a trap. And in that trap, we can do a further so-called evaporative cooling step and bring them down to a state of matter known as a Bose-Einstein condensate. This was a technique developed by Carl Weinman and Eric Cornell and Wolfgang Ketterle in the late 90s, early 2000s, which also received a Nobel Prize. And the miracle of this is after you've done this evaporative cooling, which works just the same way as when you put your coffee cup on the counter and the hot stuff jumps out, leaving your coffee colder. Here we put the atoms in a trap and the hot atoms jump out, leaving colder atoms behind. We end up with ensembles of atoms that have temperatures measured in nanokelvin, and we further manipulate them so their temperature is just picokelvins. At which point their velocity spread is measured in units of hundreds of microns per second. That is, I have an atom, I prepare it this way, I let go of it. Its velocity is defined to within 100 microns per second, slower than an ant will crawl, which is kind of amazing when you consider that the atoms in this room are whipping around at 1 kilometer per second. Now, at these low velocities, per the de Broglie hypothesis or law, you expect wave-like behavior because the velocity is low, the corresponding wavelength, inversely proportional velocity, is long. And getting them cold is key to observing these interference effects. So we've cooled them down here, that's at the bottom of the pit, and then we have a process whereby we launch them up this 10-meter tower and they fall back down. And so that process involves interactions with beams of light, and we basically turn on some lasers in the appropriate way, and we give the atoms a velocity kick so that they're moving at about 10 meters per second with respect to the lab frame, and then we let go of them. They still have that ultra-cold temperature, now they're just moving vertically, and they fly up this tube and fly back down that tube. It's like if you had a fistful of sand and you chucked it up, the sand would go up and would come back down, and the sand has got such a low velocity that just kind of doesn't spread out. These atoms, the size of the clouds when they come back down to our detection region where we have the cameras to take pictures of them is like hundreds of microns. Let's see, I got one more thing to explain, and that is I'm going to make an interferometer for atoms, so how do I make it? Well, that's also done with light and mirrors. And so we have a bunch of laser beams that start at this location. We shine them down, they hit the floor, they bounce back up, And due to the way we configure the interaction, and I'll explain this on a subsequent slide, we precisely manipulate the atomic wave packets. We coherently divide them in two, we add momentum to them, we take momentum away, and we split them up and recombine them, all with pulses of light. And this is the mirror here that the light, that laser beam reflects off of. That's the only really special part of this apparatus. It has to be stable, pointing in the same direction. With respect to the stars, inertially, it turns out in order to see the interference fringes. And so what we actually do is we actively tip the angle of that mirror so that the beam, kind of when it retroreflects off it, always points inertially, even though the Earth is rotating. If the Earth is rotating, a laser beam would rotate with it. We have to make sure the laser beam, as the Earth rotates, stays pointed straight. And so there's a piezo stage there that makes sure that happens. This is a little more experimental detail on how we coherently divide, redirect, and recombine atoms and make an interferometer, much as you would use beam splitters and mirrors and beam splitters to make an interferometer for light. And so what we do is, as I said, we shine on sequences of pulses to the atoms. Here's an example of one of our pulse sequences. Some of the data I'll show you, we use sequences of hundreds of pulses. And each time the pulse irradiates the atom in the middle of the sequence here, what it does is it takes one of the wave packets, and I should back up a moment. This chart here plots the horizontal axis is time, the vertical axis is position. And what I'm plotting for you is the center of the wave packet, the probability distribution, which tells me where I find the atom. And the wave packet, of course, has some spatial distribution. It's about a millimeter wide, hundreds of microns wide. But the center of that wave packet has a well-defined position at a given time. And that's what I'm plotting. And because I'm building an interferometer, a single atom is associated with two wave packets as it's going through our apparatus. So here comes the cloud of atoms, and let me just think of one of the atoms in that cloud. At time t equals 0, it hits this pulse we know as a pi/2 pulse. And what that pulse does is it exchanges momentum between the photons in the laser beam and the atoms in this Bose-Einstein condensed flying cloud in such a way that it puts the atom in a coherent superposition of its center of mass state, so that the atom has two wave packets, one which has momentum. We call this 2 photon recoils because it absorbed and emitted a photon, and what that amounts to is about a centimeter per second velocity kick. And the other part of the wave packet, which was left behind in this interaction, which doesn't see that velocity kick. Now, the atomic physics details are, I don't want to go into them here, but it's just standard application of the Schrodinger equation, which describes the interaction of a beam of light with a two-level atom. And so that's our beam splitter, because this part of the atom there that has a different velocity, if I wait long enough, it drifts apart from the part that doesn't have that velocity kick. Now, we only have so much time at which you can look at the atoms, so we want to give them a little bit more drift velocity than just 2 photon recoils. And so that's where all these other pulses come in. Every time I hit the atoms with wave packets with one of those pulses, I add, in the appropriate way, 2 photon recoils worth of momentum. And so if I'm plotting the position as a function of time, and here I've subtracted out the overall sag due to gravity. These atoms are flying up and they're coming down, and I'm saying, forget about the gravitational part of it. Imagine you're flying with the mean of velocity as you're going up and coming down. You just look at the relative velocities of the wave packets. These wave packets drift apart, and then we bang them again, so they come back together, and at this point they overlap. They exit at this point. This is another beam splitter pulse, and we look to see interference between those two output paths, which is experimentally observed by detecting where the atoms are at this region of space by just flashing on a beam of light and taking a picture of them. This is about 10 meters. This splitting here, that's at 54 centimeters. And now what I want to show you is after they've been separated by the 54 centimeters, when they fall back down here, hit the final beam splitter, and then fall into the detection region, and when I take a picture, I actually see interference fringes. So this is our key data. And what I'm showing you is interference fringes, which, when I say fringes, what I'm talking about is probability of finding atoms in one location or the other location at my detection port. And those two locations are this location and that location. And I get excited when I see that the atoms flopping between one location and the next location. The only way that's happening is, the only way that can happen, I claim, is if I consider the atoms as waves, and if these waves have gone through these two paths separated by half a meter. When they come back together, if I separate them by just 1.2 centimeters, I can find relative phases between those waves where the addition of the wave function is constructive and the atoms are there, or destructive and the atoms are there. And we can, anything in between also we're capable of detecting, but I'm just showing you these two extremes. For fully constructive interference, all the atoms show up there. For fully destructive, all the atoms show up there. Now, it stands to reason the further I separate them apart, the harder it is for me to get them to all come back together. So when we separate them by ½ a meter, we don't have what we call perfect contrast. We have somewhat imperfect contrast where, but we still see oscillations between the majority of the atoms being at that position and the majority of the atoms being at that position. And for us, this is a smoking gun signature that these atoms had to be interfering as quantum mechanical particles. Now you might say, shoot, but quantum mechanics is true, so what's the big deal about ½ meter versus a centimeter? And also, what have other people done? So this data here for massive particles is the world record. We're about 100 times more spatially separated than anybody else has done in any other lab in the world. But so those are kind of nice bragging rights that you use to maybe get your data into Nature or some other journal. But as scientists, we want to know, is it worth doing an experiment like that? And so I kind of want to tell you that story a little bit on subsequent slides. You might also be thinking, well, I also know that light is comprised of a stream of photons, and a photon is a quantum mechanical object. And when I put a photon on a beam splitter and I separate it and recombine it, that photon flies over distances which are much larger than the 54 centimeters. And I would say, if you're thinking that, that is definitely a legitimate and interesting thing to think about. And it's very interesting, in my view, to compare the quantum mechanics of photons, massless relativistic particles, and those of massive particles like atoms, and how quantum mechanics treats them in terms of what the predictions ought to be. So what do we learn when we separate an atom by ½ meter? Well, there's a lot of effort all across the world right now trying to figure out how macroscopic we can make a quantum system. And by macroscopic, how far apart can we separate it and recombine it? How massive can the particle be? I showed you an atom. People are actually in Vienna. They're interfering molecules, fairly substantial molecules. And one of the experiments they have on their docket is to interfere a virus. So you can make something that may be alive, separated and recombined. They're doing those big stuff over much smaller distance scales, often measured in hundreds of nanometers. And also over what time scale they're separated. There's all these different experiments happening, and you kind of want to have some way of comparing them all, and some notion of how macroscopic, how big the quantum state you're making really is. And so these theorists in Vienna, Nimrichter and Hornberger, in 2013 did a really interesting set of theory work where they created a framework that allows us experimentalists to kind of compare the macroscopicity of one kind of quantum experiment with another. It might be that it's more interesting from the point of view of fundamental tests of theory to interfere a molecule over 100 nanometers than an atom over a ½ a meter. And their theory, by the way, only applies to massive particles, not to photons. And so taken this way, I don't really have time to go into the axes on this plot. My point of showing this is just kind of show you that people are thinking about this. And our work, the stuff I just showed you, it constrains quantum mechanics in a way shown by this green line. And what it does for certain parameter ranges on that plot, which kind of tell you about the separation of the wave packets and so forth, we're setting the most stringent limits on macroscopicity by many orders of magnitude. So it turns out it does seem like it is interesting to be just exploring the interference patterns of atoms at these distance scales. Well, you might be asking, well, shoot, but what's the point? What would happen if quantum mechanics was wrong? How might quantum mechanics break down? A lot of people thinking about that. There's a lot of kind of crazy theories that have been proposed for a long time. I want to tell you about one of them, which was resurfaced back just a few months ago and analyzed our data in the context of this theory. When we do physics, when you do engineering, we make fundamental assumptions about space and time. Homogeneous, isotropic, time progresses uniformly. But when you look at the fine-grained scale, Planck scale, 10 to the minus 34 meters, you start to think that maybe space really isn't homogeneous. Maybe it's grainy. Maybe time isn't continuous. Maybe it ticks in a funny way on certain distance scales. And maybe quantum mechanics of massively separated objects might be sensitive to these kind of perturbations. It turns out we have to have extreme control over the paths of the atoms to get them to come back together and interfere constructively. And if the velocity of one of those wave packets changes by nanometers per second, that's enough to kind of wipe out the coherence. And so we make this experiment by the fact that we see those fringes makes very good tests of anything that's going to go in there and shake around the atoms as they're propagating. And it may be the very nature of space-time itself that's doing this. This Ellis model imagines a gas of wormholes that are flying through space. And this was taken seriously until the early 90s when some people shot this theory down. And these wormholes, according to this phenomenology, collide with the atoms and give small momentum kicks and ruin the interference pattern. And so there's a bunch of complicated math these guys did and basically showed that the data I just showed you dramatically constrains these sort of wormhole theories. And to put these theories in context, there's been a lot of thought about the quantum mechanics of black holes and things recently and over the past 20 years. And this was one of the early types of forays into quantum and gravity by people like Lenny Susskind when they were trying to figure out, and they still are trying to figure out, the quantum mechanics of black holes. I'm going to change gears a little bit. Oftentimes, when you build an interferometer, you build it to measure something, not just to learn something about structure of space and time. And that's kind of the reason why we're building these apparatus. By looking at the interference fringes, and assuming now the interference fringe is something stable, we can learn something about the relative paths that the two wave packets take. So what do we learn? Well, the theory for calculating the relative phase shifts between atom wave packets as they propagate through space and time is well defined. And it's been articulated since the beginning of this field, and it just involves, again, systematic application of Schrodinger equation. And again, I'm not here to explain these equations to you, just to say that those equations exist, and you can go in and actually calculate what the relative phase shifts for the two paths are. So you might ask, well, what drives the relative phase of those two paths? Well, anything that changes the velocity of the two paths is going to lead to a phase shift because of the Rowley relationship. What changes the velocity? Well, how about the acceleration due to gravity? That's something that's, as those atoms are flying through the apparatus, their velocity is changing with time. The phase, the wavelength is changing with time. That turns out to lead to a huge phase shift at the output of the interferometer. If the interferometer is rotating, there's another phase shift associated with that, the Coriolis effect. And there's a whole list of phase shifts that you can calculate along these lines. Bottom line is these devices are extremely sensitive to inertial forces, rotations and accelerations. And that's why we use them, we build sensors with them. I'll show you a sensor in just a minute. This is one of those sensors, which is to say that, and I want to maybe go to this list first. When I do that calculation, you say, well, what do those phase shifts look like? We call a table like this affectionately the term list. And what I'm describing here is all the different ways that I can get relative phase at the output of the interferometer. And for the highly engineered sensors we build, these term lists have hundreds of terms. And I just put in a simplified one here to show you some of the most dramatic shifts. This K is the propagation vector of the laser beam that we use to bat around the atoms. G here is the acceleration due to gravity, and T is the time between, basically the time of flight between the first beam splitter and the exit beam splitter. And I'll just focus on this top term and point out something amazing, that in that data I just showed you, as the atoms are flying through the interferometer, about 10 to the 10 radians of phase evolve between one path and the other before the wave functions overlap. So if I measure the phase of the wave function precisely, I'm basically, and I can count which fringe I'm on, I basically have an awesome accelerometer, an awesome way of measuring accelerations, or if I'm on the Earth, the gravitational field. Let me just put an order of magnitude in there. 10 to the 10 radians, and typically we can, on a single experiment, resolve a phase shift to about a 10 to the minus 3 to 10 to the minus 2 radians. It says on a single shot, we are in principle capable of resolving accelerations at the 10 to the minus 12 of little g level, 10 to the minus 12 to 10 to the minus 13, just a single realization. And that's, I mean, okay, there's a small number. How small is it? Well, the gravitational acceleration of two of you guys sitting next to each other is 10 to the minus 9 a little g. So it means if somebody's drinking a cup of coffee next to you, their mass has changed by enough that the gravitational interaction would be about 10 to the minus 11 of little g or something like that. That's still that, and that would be detectable with a sensor like this. So it kind of makes you want to build these sensors, maybe not on that grandiose scale. And so this company, Ellis, which is literally just down the road, is building smaller versions of these sensors for real-world guidance, navigation, and control applications, and also geodetic applications, studying of the Earth's acceleration due to gravity and so forth. And in this can here is a much smaller atom interferometer that's measuring the acceleration due to gravity. And this is some data from that sensor. This is time in kiloseconds, and one of these oscillations is about a day. And these variations in gravity are the well-known variations in acceleration due to gravity due to the motion of the Earth and the Moon. This is about 10 to the minus 7 of the 9.8 meters per second squared of gravity. Just to point out that, yeah, these are really sensitive sensors, and when you build them on these grandiose scales, they become extra sensitive. So what are we going to use that extra sensitivity for? And this is data that's just started rolling in the past month. Well, I'm in the physics department, so what basic science might we do with this? People are interested in answering at a precise level the age-old question: does the brick and the feather, do they fall at the same rate? The Leaning Tower of Pisa experiment, the Galileo experiment. In modern times, it's known as equivalence principle measurement, and the equivalence principle is a foundation for Einstein's theory of general relativity. And it's theoretically interesting, I'm told by my theory colleagues, to probe this principle at the part in 10 to the 15 to part in 10 to the 18 level, which is to say, as the objects are accelerating together at basically the acceleration due to gravity, there may be some spurious interaction due to particles we know nothing about that make it so a rubidium-85 atom accelerates at a slightly different rate than a rubidium-87 atom because they have different nuclear composition. And so that's the experiment we're doing here. We have two ensembles of Bose-Einstein condensed laser-cooled atoms that have been launched and subjected to a bunch of pulses that are flying up and down this tube, both opening up and closing interferometers. And then we measure simultaneously the phase shift from rubidium-85 and 87. By comparing the phase shifts, we make a comparative measurement of their acceleration due to gravity, and then we seek to understand whether the observed acceleration due to gravity is the same for one isotope or the other. Now, I don't have results to formally discuss, but I do have some preliminary data show you kind of what these action shots look like now when we're making a simultaneous measurement of the co-acceleration of 87 and 85. This is a picture in false color. As my colleagues joke, everything looks better in false color. So in false color, rubidium-87 in the upper part of the camera port, rubidium-85 in the lower part. This is one output port of the 87 interferometer. This is the other output port, same for 85. And we introduce a phase, what we call a phase shear, across the interfering waves so we can precisely measure the phase. This is like what happens if you misalign an optical Mach-Zehnder interferometer. You see fringes. And basically, by comparing the phase of these, this is a lot of atoms and this is a few atoms. By comparing the phase of those peaks to the phases of those peaks, we can measure the relative phase and then get a handle on the equivalence principle. The data I'm showing you here right now is good to about 12 digits, and we think that when we get this apparatus all tuned up, we're going to have 14 digits of sensitivity or more. And at that level, our theoretical colleagues start getting interested in these results. Thanks. Let's see. So where do really interesting things happen? Well, people think the really interesting stuff is going to be at 16 digits. The world record for equivalence principle right now is in the University of Washington gravity group, where they measure equivalence principle using torsion pendula to 13 digits, and they're pushing into the 14-digit level. And so we're hoping to at least have a measurement that's competitive with what they're doing and complementary in the sense that we're using this completely quantum mechanical method for making the measurement. What else does equivalence principle measurement tell you? Well, what's the impact of EP being true or false? And so here there's a lot of recent theoretical work motivated by the fact, by cosmology. Basically, there's dark matter out there, and we don't know what it is. And certain flavors of dark matter lead to equivalence principle violating interactions that we might see in our lab. And so this is a chart from one of my colleagues, Peter Graham at Stanford, that shows the possible impact of the measurements we're doing right now on some of his favorite equivalence principle violating theories. And again, not going to explain the axes, just to say that this yellow region is what we know to be excluded right now, and the kind of data we're taking is going to further push the bounds on the possible validity or lack of validity of these obscure theories about dark matter. I want to change gears to some more wholesome physics. So you probably all have seen in one form or another this data, which is the unbelievable data that was taken by the LIGO collaboration for their first observation of gravitational radiation. What they did was they built two conventional optical interferometers at two regions in the United States. And the idea is that if black holes spin and merge at way far away, they give rise to perturbations, ripples in space-time, which propagate at the speed of light through space-time to us here on planet Earth. And these space-time ripples basically have the effect of stretching and contracting space as a function of time in such a way that if you build one of these precision interferometers, it can be observed. And so just to take you, if you haven't seen this data, take you through some of their signals. This is the output of one of the interferometers, and this is the output of the other interferometer, that one there and that one there. And when you see those fringes, when you see that shaking, that means that something came and changed the path length of one of the interferometer arms with respect to the other, that something being a gravitational wave, and in such a way that you can observe the cataclysmic event, which in this case was way far away, two black holes coalescing. And so I just explained that I'm building interferometers, and the interferometers I'm building, I think, are going to be very sensitive. And so you might ask, could we see gravitational radiation in a way that's similar to LIGO, but now using atom interference? And if we could, why would you want to build an instrument like that? And so I'll spend just a few minutes kind of describing our thinking on that. We haven't built anything that's nearly as sensitive as this LIGO instrument, but we think that a space-based instrument holds promise for observing certain types of gravitational wave sources. And here my philosophy is the following. This was the breakthrough discovery that taught us that observing the physics community and the astronomy community and the astrophysics community, that observing gravitational waves is really interesting. And you go back in time, you say, well, we know that using telescopes to look at the cosmos is also interesting. And right now, when you do optical astronomy, there are lots of different telescopes that you build depending on what you want to look at. So as gravitational wave astronomy progresses as a field, I think it stands to reason that there are going to be a diversity of telescopes that you're going to bring to the table for making scientifically interesting observation. So here's a plot generated by Susanna and colleagues that basically traces the evolution of the black hole merger that I just showed you through time. And what's happening in the LIGO signal is that the LIGO antenna only captures the transient signal for the very final moments of the merger, when those black holes are spinning really quick and then merge. That's when you see blips in the interferometer. Well, in this situation, those black holes are spinning slowly before they hit this cataclysmic event here for a long period of time. And it's interesting to go and look at these black holes in this region of parameter space before they finally hit their merger situation. How might you build an antenna that is capable of detecting these low-frequency perturbations? Well, the world has been thinking a lot about that, and that's where I think our atom interferometer detector may have something to say. When I say the world's been thinking a lot about that, there's a planned ESA mission, and the NASA is looking like it will participate in that, that is designed to detect very low-frequency gravitational waves. This is frequency, and this axis here is the amplitude of the gravitational wave. And you notice that this antenna, this telescope, can see the very low frequencies. LIGO can see the very high frequencies, but maybe you want to see these intermediate frequencies. So this is the antenna we propose to build with atoms. And I'm showing you kind of a theory view of something that we published in this paper a number of years ago. This is the space-time diagram for the positions of wave packets at one region in space and another region of space. This is this region of space. Now I want to be separated by about a gigameter, 10 to the 9 meters, such that if a gravitational wave comes rolling through this intervening space, that will lead to a relative phase shift of this interferometer with respect to that interferometer that I can observe, very much like the differential phase shift that we're observing right now in our equivalence principle work. The only difference is these interferometers now are separated by a long distance, and I have to correlate the phases across that baseline. It turns out this is a pretty good way of detecting a gravitational wave. If you're building instruments, what we are essentially proposing doing is this is a LISA instrument, which is very good for the ultimate low frequencies. We're proposing replacing a macroscopic proof mass, which sits inside the satellite and which has recently been verified by the LISA Pathfinder collaboration, spectacularly verified, with a cloud of atoms. And due to the atomic physics processes, it turns out we can build this antenna with just 2 satellites. The LISA configuration requires 3 satellites, and from a system engineering perspective, we think this may be favorable. And if you want to think more deeply about this, it turns out the atoms are serving as precision proof masses and position references, and the lasers that we use to interrogate the atoms are providing a really excellent ruler by which we're measuring the time evolution of their 2 distances as the gravitational wave comes through. And if you say, well, how good is this telescope? The telescope is, I characterize it by its frequency and its strain response, how big of a wave it can measure. This is what the LISA antenna can do, and this is what we think the antennas that we are envisioning can do. And if you want to take that a step further, there's some new ideas we have out there where the LISA strain curve is sitting up here, and what we want to do with atoms is a couple of orders of magnitude better. So this is probably the generation of telescopes, 2 generations away. LISA has to be built first, but eventually I hope that we'll be starting to build these gravitational wave detectors with these atom sensors. More practical applications? Well, I'm measuring, when I build a gravitational wave detector, I'm measuring perturbations in space-time due to gravity very precisely, in that case due to a gravitational wave. If I have a satellite in low Earth orbit, I can do something more mundane. I can look at the perturbations in the relative positions between 2 clouds of atoms, this time separated by meters, not 10 to the 9 meters, in the same way by building 2 interferometers and subtracting. And it turns out that makes a very good differential acceleration sensor, which I can use to characterize the Earth's gravitational field and perturbations in this gravitational field. And this is considered interesting because the perturbations in the gravitational field, as observed from orbit, tell you a lot about the mass distribution on Earth. And we're interested in the mass distribution because some of that mass is water. And as we know, due to climate change, that water is moving around. And so ice is melting in one place, it's going someplace else. And how can we figure out where it's going? There's a guy at Goddard, and there's some other people at JPL looking at this. This data here is from this analysis from Scott Lutke's group at Goddard, where they're actually looking at the gravity gradient signals of water table. And this is one of the maps they generate, and they kind of show you the gravity contrast from water as moving around. And so we're with NASA Goddard building an instrument which would be a prototype for one of these space-based gravity gradiometers. So I have 5 minutes left, and I want to just in this last 5 minutes change gears a little bit. I started the talk by telling you about a story about macroscopicity in quantum mechanics in terms of distance separation. I want to finish the talk by telling you a different type of macroscopicity, that is, how can we make states and manipulate states that are quantum mechanical but contain large ensembles of atoms. And the state I'm going to tell you about is one where we have collections of atoms, thousands of atoms, all glued together in a fundamentally quantum mechanical way, that so-called entangled states that are doing something very useful for us in the context of interferometry. And so my intro to this last subject is, let's talk about noise for a little bit. When we go and build our interferometer and look at an interference fringe, we don't measure a perfect phase. We always get a little noise on top of that fringe. And I illustrate that schematically here. If I'm building an interferometer, I don't care what interferometer it is, I scan the phase, I'm detecting some number of particles in an exit port, and there's always some noise at a particular phase. Here I've frozen this cartoon at this particular phase value and plotted a distribution of the number of particles that I detect, photons or atoms, at an output port. And it fluctuates. It fundamentally has to fluctuate because what I'm doing is I'm collapsing wave packet when those two interfering photons or atoms come back together, and it's a fundamentally statistical process. Now, that collapse happens often in a way where the statistics between one particle and the next are completely uncorrelated, and it gives us what's called shot noise. And there's well-known theory which predicts the amount of noise you expect to see for the number of particles you have coursing through your interferometer. And to make a long story short, using kind of laser and atomic physics techniques, we are now manipulating that noise in a fundamentally quantum mechanical way to reduce the noise at the output port of the interferometer. And just to show you that in data, this is the output port of an interferometer, which was tuned to operate exactly at that mid-phase point that I showed you on the previous slide. And if I use just regular atoms, not fancily entangled or correlated with some tricks I don't have time to tell you about, if I measure the fluctuations, I get a distribution shown here in blue. And those fluctuations, for virtually every interferometric sensor that's built today, those shot noise fluctuations fundamentally limit the sensitivity of that instrument. Now, using quantum entanglement tricks, we now have manipulated this ensemble of atoms so that those fluctuations are 10 times narrower. And it stands to reason if you're associating with the mean position of that distribution a phase and you care about measuring the phase, having a narrower distribution really helps you in your precision measurement. And we demonstrate that in this data by applying a tiny phase shift to this interferometer that shifts this distribution from an output of that number of atoms to this number of atoms. This is the number of atoms at the output port, and this is the probability of observing that number of atoms. This entanglement is really helping us. Now, this entanglement, this correlation of creating these correlated states of atoms, which again we do with lights and mirrors, is doing something amazing to a cloud of otherwise 10 to the 5 atoms which are non-interacting. What it's doing is they're making them fundamentally linked in a quantum mechanical way so that when I make a measurement, if I measure an atom here, somehow that affects the wave function of an atom over there in such a way that when I measure them all, I can't, they're correlated in such a way that I can't have fluctuations bigger than what we observe there. I've been using this word entanglement a lot. I'll skip through this. We do this with a cavity. That's what the apparatus looks like. If you use this word entanglement a lot, what do I mean by that? Well, I mean when I try and write the wave function for all those atoms, and if you've had that quantum mechanics course, you write of one particle, you write its wave function down, and then in the Hilbert space, you write the wave function of the next atom down and the next atom down. If they're uncorrelated, it's straightforward to you to write the wave function for all those 10 to the 5 atoms down. Once you do this, we call it a squeezing operation, which is squeezing out the noise. You have trouble writing down that wave function in such a way that you can separate out the contributions from each atom and factorize them each atom independently. In fact, for this data, this analysis shown in this plot says that the wave functions for these atoms are correlated in such a way that I can't think of the atoms in smaller groups than 1,000 independently. They're correlated in clusters of at least 1,000 atoms. This is like a world record for quantumness of ensembles of atoms. And what's interesting, if you've read about quantum computers and things like that, it's this very entanglement property, which is thought to be going to be useful for speeding up computation. Well, for building sensors, it's also useful. And if by reliably entangling the particles, I can dramatically reduce the sensor noise, making a better sensor and actually making these fancy ideas of quantum mechanics useful. And so this work is demonstrating macroscopicity in a different way. I now have 1,000-atom quantum systems truly behaving as quantum. At that, I have to thank the people in my research group and my theory collaborators, and you guys for your attention.
Thank you very much. Thank you. So we have time for a few questions. If you have a question, please raise your hand, wait for the microphone, and ask one question only. Thank you. There's up front here.
Thank you. Thank you for interesting talk. You mentioned these very sensitive accelerometers based on atomic interferometry, but they all require this cryogenic, very low temperature sort of operation, right? So you cannot make them very small. They should be heavy, they should be bulky. So how can you put something that big to satellites or like?
Yeah. So when we say ultra cold, the only cryogen I'm using is laser light. So I need a single frequency laser, which is smaller than the semiconductor laser fast is smaller than my thumbnail, and it's the interaction of the laser light with the atom cloud that reduces their temperature. And so the smallest sensors now are approaching the size of my fist. I showed you that gravimeter, which is about the size of a 2-liter Coke bottle. And as we kind of start engineering these and replace kind of bulk optics with integrated photonics, which we're now manufacturing with some partners in the Valley, and state-of-the-art semiconductor laser sources, the size of these sensors is being crushed. They're really becoming small. In fact, there's some, AOSense and my interests aren't in making them tiny, 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 like competing with MEMS sensors. We want them to be big enough to be high performance, but we have gyroscopes now that are about this big that have performance figures of merit that are really pretty extraordinary. So it's all about engineering with optics, and that's the main technical challenge. There's a little bit of new engineering knowledge that we have to gain, figuring out how to make reliable sources of atoms and all the rest. Much of that draws on some work from the atomic clock community in the 50s. Another way of answering your question is you're comfortable with going out and buying an atomic clock from used to be Hewlett-Packard, and now it's Microsemi, that's rack mounted, that and has a beam of atoms in, and it's interrogated. Kind of what we're doing is very similar. We do not need liquid helium. Yeah.
If you can entangle 1,000 atoms, any chance of using this in quantum computing in the near future?
For what?
Quantum computing? Quantum computer?
Oh, that's an interesting question. So what are the links between, the field I just discussed is receiving a great deal of interest right now. It's called quantum metrology, and that's using entanglement to improve performance of sensors. But we all sort of also want to build a quantum computer, and so what's the link between this kind of entanglement and the entanglement you need for quantum computation? Well, I view it as a baby step towards a quantum computer. So a quantum computer, you have to go in there and reliably entangle, almost deterministically, I should say, the wave functions of each and every atom in a way that you sort of understand. Here I have this grab bag of atoms that are sort of magically being entangled, but in a way that I have even trouble writing down what the wave function is. So there's a big step between what I've just demonstrated and the type of entanglement you need for a quantum computer. Nonetheless, if you follow this field, there's a lot of discussion about what makes a good qubit for a quantum computer, how you're going to error correct that qubit, and so forth. And some of these cavity atom ideas are interesting players in that discussion, but it gets pretty technical, and you have to talk about the gate fidelities and things like that, and it boils down to a bunch of technical details that maybe aren't, they're surprising on first blush. So part of my program is to figure out what role this type of entanglement might have in quantum computation, and I say that I'm much more optimistic about other systems than that for quantum computation. Yeah,
Okay, so please join me in thanking Dr. Kasevich for an excellent talk. Thank you.